In this section, we're going to work with parametric equations. And parametric equations are equations used for describing a curve in the xy plane where you base the value of the x-coordinate and the y-coordinate on a third variable, which we call a parameter. And we usually use t. So we have x as a function of t and y as a function of t. So there's two equations, one for x and one for y. But when we graph in the plane, we don't graph t, we're still graphing x and y. T is often time in the application of these in applications of these problems, so that like maybe you could talk about the position of a vehicle or a bus or something like that with respect to time. You could graph its coordinates at different times then, for example. Okay, so let's look at an example. In this first example, we want to graph the curve defined by x equals 1/2 t, y equals t squared minus 3. And then there is a restriction on the values of t. T varies between -3 and 3. So when we do this, we kind of think about, well, where does this object start? What are its coordinates initially? And where does it end? And we often will indicate the direction of the motion. So if if it's a car moving, we'll indicate where it's going, right? We'll just use arrows for that. And this is called the orientation of the curve. So if you're asked to indicate the orientation of the curve, then you're going to use arrows, and I'll show you how to do that. Okay, so let's do this one by plotting points. There's actually a couple of ways we can do it. One way is to think about plotting points. The other is to eliminate the parameter and look and see if we get an equation that we recognize the graph for. And I'm going to show you both ways here. First, let's just think about what the x and y coordinates would be given different values of t. So actually I want to put t first. And t is going from -3 to 3. So, and this is continuous. T can be any number between -3 and 3, such as 1/2 or 0.0025, right? Any number in here. I'm just going to use the integers because those are easy to use. So I'll use -3, -2, -1, 0, 1, 2, 3. Let's get ordered pairs for all of those values of t. So when t is -3, then to get x, you plug that into this equation. We'll get -3/2 for x, and y will be -3 squared is 9. 9 minus 3 is 6. For -2, x will be -1. 1/2 times -2 is -1. Y will be -1 squared is 1. 1 minus 3 is wait, what did I say? Yeah, 1 minus 3 is -2. For -1, we'll get -1/2. And then, oh, something felt wrong. It's because I was plugging in the x instead of the t here. I just realized, yeah, because now when I plug in 1, I get the same thing. This should be the -2. I'm sorry. I accidentally put in x. I should be putting in t. Make sure I look at the right number. 4 minus 3 is 1. There we go. That makes more sense. When t is 0, I'll get 0 for x and -3 for y. 0 minus 3. For 1, I'll get 1/2 for x, and then 1 minus 3 is -2. Same thing I got for when t was 1. For 2, x will be 1. 4 minus 3 is 1. Y will also be 1. And then for 3, we'll get 3/2, and y will be 9 minus 3 is 6. All right, so these are my ordered pairs, okay, that I graph as usual. T doesn't actually get plotted in here. So -1.5, 6, -1, 1, negative 1/2, 2, or negative 2, excuse me, 0, negative 3, 1/2, negative 2, 1, 1, and 3/2, 6. So 1 1/2, 6. Because of the restriction here, we aren't going to extend beyond where t was negative 3 and 3. So this starts here. This is the initial point, or initial position. And it goes down here. You can see this is a part of a parabola, right? With the symmetry. Looks like, or at least it looks like a parabola. And then this would be where it ends. So this is for t equals negative 3. This is for t, I should say when, equals positive 3. And the orientation of the curve then, since it starts here and goes here, this curve gets traced one time. So we don't put an arrow here like normally, like we're used to graphing, we put arrows on the tips. We don't. We have these end, but these arrows is just saying the curve gets traced in this direction. All right, so we're done with the problem, but I want to redo it now by eliminating the parameter and seeing the equation we get in x and y. So our objective is to get an equation in x and y, which is what we're used to working with, right? So let's eliminate the parameter. So when you do this, you just look at, well, okay, would be easy to solve for t, and you can pick this t here or t here. This one is obviously easier. Here I'd have to bring in a square root. So t, if I use x equals 1/2 t, that implies that t is 2 times x. And then you're going to plug that in to the equation y equals t squared minus 3. So replace the t with 2x. That gets the t out of the equations. So then y equals 2x squared minus 3. So y equals 4x squared minus 3. And now we can see that's a parabola, right? Which we already could tell from the graph that it was a parabola. Now, we didn't actually graph this whole entire parabola. We only graphed this parabola for x. The values of x go from negative 3/2 to 3/2. So this is for negative 3/2 less than or equal to x less than or equal to 3/2. So if you're asked to eliminate the parameter, you should include any restrictions. Otherwise, if you just say that this is equivalent to y equals 4x squared minus 3, that is not true. It's y equals 4x squared minus 3 for x between negative 3/2 and 3/2. There's, a cutoff. This doesn't go on forever. So you do have to, it's not just a purely, doing a substitution and you're done. You do have to think about what's going on. If we hadn't graphed this, how would we know these were the restrictions? If we hadn't done all of these ordered pairs, well, we'd have to plug in the lowest value of t for x and the largest value of t for x to get these numbers. Then we would know the restrictions. Okay, so when you do this, again, it doesn't matter which equation you use to plug into the other. Just solve for t, whichever one's easier. Maybe they're both equally easy, so just toss a coin. But this one is clearly easier. If you use this one, you have to be careful because of the square root, and there's a plus and minus involved when you use the square root property. So take the simpler one. All right, the next problem, here we have another set of parametric equations. This one is asking us just to eliminate the parameter and indicate the orientation of the curve. So clearly, this is the easier equation to solve for t. This would be a challenge. So y equals t minus 1 implies that t equals y plus 1. And then we're going to plug that into x equals t squared minus 2t. Unfortunately, we have two places to substitute y plus 1 in, but that's okay. This is not that hard with the algebra, right? So y plus 1 squared minus 2 times y plus 1. X equals y squared plus 2y plus 1 minus 2y minus 2. These cancel. X equals y squared minus 1. If we want to put this in a form of like the conic section treatment, we want to isolate y squared, so x plus 1 equals y squared. And then, well, I'm getting ahead of myself. I didn't mention, this is a parabola, right? We have a y squared term. It's a parabola that's going to open on its side because this is not a function of x. So again, yes, the conic section treatment, I move the 1 over here. Y squared equals x plus 1, and then I can see the vertex is negative 1, 0. You could also solve for y if you wanted to do probably what we would have done back in college algebra. Y squared is x plus 1, so y equals plus or minus the square root of x plus 1. So you would take the square root function and shift it back 1, and then you would end up here, which is the vertex that we got, and then you'd have the upper half of a parabola would be the positive square root, and then the lower half, so I should go out 4 up 2, down 2. This would be the minus square root of x plus 1. Now, what was I going to say? You can also use the, find the focus and use the, the double P to get 2 points. You could use that to graph it as well. What was I going to say? Oh, we have to think about now the restrictions on t, which there are none. T goes from negative infinity to infinity. So this will keep going on forever. However, I don't want to put we won't use arrows like this like we're used to. We need to think about, where is this going? Is this tracing like this, or is it tracing like this? And sometimes things keep tracing back and forth forever and ever. We have to think about those things. So what happens here, or how you can figure this out, is think about t going from a small number to a big number, and just pick one of the variables to think about. And I would pick y because y has a simpler equation. See what happens when when t is small, y will be small. When t is large, y will be large. That's telling you the y coordinates are increasing. They're getting bigger. And on the parabola, these points have a smaller y coordinate than these. So the orientation of the curve is actually like this. Now you can do this for x as well. See, what's happening for x is, so here, let me write that down. So y values are increasing. As t increases, let's just say increases. But what's happening with x is, notice the way the curve goes, if you're looking at it just for x starts big, it gets smaller, it reaches a minimum at -1, and then it starts to get big again. And that's what's happening here, because the t squared term, when t is a large negative number, you get a t squared is positive, so you get a large positive number. This is stronger than this term. This has a little effect, but you have to basically just look at the t squared. Then as you get t gets close to 0, x will get smaller. Once you get t gets beyond 0, then we start to increase again. So, well, I should be careful. It's not necessarily at 0, right? X is 0 when t is 0, but it's near there. We'd have to solve this to find the minimum value. We won't get into that, but I just want you to, think about, well, what's happening to x? So as t gets bigger, x at first is big, then it starts to get smaller as t gets closer to 0, and then as t gets bigger again, it starts to increase. Okay, let's move on to the next one. In this problem, graph the curve represented by x equals cosine t, y equals sine t, and t varies from 0 to 2 pi inclusive. Well, these are the definitions of the trig functions, right? X is defined as the cosine function and y is defined as the sine function. And in fact, this is the parametric definition of the unit circle. So if we took, to eliminate the parameter here, you need to use a trig identity because there's trig functions involved. We wouldn't want to solve this for t. Instead, we want to relate cosine and sine. And of course, the simplest relationship is the Pythagorean identity, that cosine squared t plus sine squared t equals 1. Well, cosine of t is x, and sine of t is y. And so that's the unit circle. And what will happen here, if you think about t going from 0 to 2 pi, you can see where this starts. Cosine of 0 is 1, sine of 0 is 0. The first, we'll make this 1 unit. So the first point is here. Then t goes to pi over 2, cosine will be 0, sine will be 1. And then at pi, cosine is -1, sine is 0. At 3 pi over 2, we'll get cosine is 0, sine is -1. And then back to 2 pi, you're back to the initial point. So you start here when t equals 0, and you go around the unit circle 1 trip around. Whoops. So there's 1 trip. And that starts at 1, 0 and ends at 1, 0. If this went to 4 pi, it would be 2 trips around, right? If this goes to infinity, it just keeps going around and around and around and around. So you have to look at this restriction to describe the curve. How the curve is being traced, I should say. All right, next problem. How many do we have? All right, eliminating the parameter, we've got the exponential function base e. So x equals e to the t, y equals e to the negative t, excuse me, and this is for t bigger than or equal to 0. Okay. So, so let's go down here. So if x equals e to the t and y equals e to the negative t, we want to solve for t. I guess I'll use this one because it's a little less complicated. This would imply, as we have to think back to college algebra now, that t equals the natural log of x. Remember that natural log is a base e log, so e to the t equals x is equivalent to t equals natural log of x. So in y equals e to the negative t, plug this in, this implies y equals e to the negative natural log of x and the negative here, this is a -1, can come up as a power. These are inverse functions. They'll cancel each other out, so we just get x to the -1, which is 1 over x. So y equals 1 over x. And, that is, if you recall, hold on, let me make sure this is on the screen. That graph looks, it's a rational function. It looks like this. But we have to think about which part of this graph we have because we have a restriction here. It's not necessarily the whole thing. So let's let t equal 0 and maybe a couple more values just to see where the graph is. So x, y. When t is 0, e to the 0 would be 1. So x and y are both 1. When t is 1, we'd get e and then e to the -1, or 1 over e. And then when t is 2, we'd get e squared. And then this would be e to the -2, or 1 over e squared. So 0, 1 is the first point. Or I mean 1, 1. I'm sorry, 1, 1. That's our initial point. Then we'd have e and 1 over e on the graph. So e is about 2.7, of course. And 1 over e, I need the calculator for, about 0.4. So 2.7 and then 0.4 is about here. So this is e, 1 over e. And remember this graph goes 2 would be, for 1 over x, if you plugged in 2, y would be 1/2. This is lining up along there. 3, we'd get 1/3. And 1/3 is less than this 1 over e was about 0.36. All right, when we plugged in 2, 2 is e squared. E squared is about 7.4. And so that's, well, that's going to be off my graph quite a ways, isn't it? Because that only goes up to 4. So 7.4 and 1 over e squared. Whoops. Get out of there. Quit. I'll just clear that out. 1 over e squared is about 0.14. That's going to be way over here. Which, it at least verifies to us that this is approaching the x-axis. And so what we're getting is just this part of the curve. And this keeps going, t keeps getting bigger and bigger. As t gets bigger and bigger, x will get bigger and bigger, but y will get smaller and smaller because it's going to a negative power. So the orientation of the curve is like so, and this, whoops, doesn't come back up. It just keeps approaching the x-axis. So this keeps going. So to be complete here, y is not just 1 over x, it's only 1 over x for, and now we can see on the graph, x will be bigger than or equal to 1. Okay, we have one more of these. So this one again involves trigonometry, so we want to use an identity to eliminate the parameter. We don't want to use inverse functions. We want to use an identity. Clearly, again, the identity that relates sine and cosine is sine squared t plus cosine squared t equals 1. So sine of t will equal y over 4 in this case instead of y. And cosine of t is x over 3. So we'll replace sine with y over 4 squared. And cosine of t is x over 3, and again squared, square those terms. And so we get y squared over 16 plus x squared over 9 equals 1. And if you did your homework in chapter 4, you know that's an ellipse. And it's centered at the origin. All right, so we eliminated the parameter, but again, do we have the entire ellipse or just a part of it? So now we need to look at this to determine that. This ellipse, you'd have the major axis would go square root of 16 is 4, so be of length 8, and then our other points on the parabola would, or excuse me, the ellipse would be at 3 and negative 3 for x values. Right? This would be the ellipse, but which part do we have? Well, this part of the ellipse is for t from pi to 2 pi. So just plug in pi, start with pi. Cosine of pi is negative 1, so x would be negative 3. This is the initial point. Now, do we trace this way or do we trace this way? Well, I would just go to 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. So y will go down to negative 4 now. So we're tracing like this. And then when t is 2 pi, cosine is 1, so we've got x is 3, and y is 0. So we're back, or we're up to this point, and that's it. That's the end. Ending point, or the terminal point. And it does not keep going. I don't want that arrow to make it look like it's going to keep going there. So this ellipse, the correct answer, if you didn't have this part, you'd lose a couple points. This would be for, this is equivalent to this for x between negative 3 and 3. But that's actually not even enough information because the entire ellipse is between negative 3 and 3 and negative 3 and 3. So we also need to say and y between negative 4 and 0. That's a pretty tricky one. Right, and so with this part here, well, I guess we could actually probably leave this part off. And this is the part that where you really show the restriction, right? It's not incorrect to include that though. Right, the next example, we are going to find parametric equations for an equation in xy form. So we want 3 sets of parametric equations for the line of slope 2 that passes through the point 3, 5. It doesn't really matter what you choose when you do this, but let's write the equation first. I'm getting ahead of myself. So slope is 2 and passes through 3, 5, so let's use point slope form. So y minus 5 equals 2 times x minus 3. And you can leave it in that form, or it might be easier for you to solve for y, and so put it in slope-intercept form. This implies y equals 2x minus 6 plus 5 would be minus 1. So now what I would do, because y is a function of x here, is just write formulas for x in terms of t. Now, if you want this to be truly equivalent to the entire line, you need to pick a formula that doesn't restrict x in any way. So my first one here, the easiest thing is just to let x equal t. And then y will be 2t minus 1. That would be one set. Okay, so there's answer 1. 2, just pick another formula for x and then plug that formula in and solve for y. But what I said before is very important. Don't pick anything that restricts x if you want this to be equal to the entire line. So I wouldn't let x equal the cosine of t, because then x is restricted between -1 and 1, and you wouldn't have the entire line, you'd only have the part of the line that's between -1 and 1. So maybe pick something like x equals t plus 5, then x will take on all values. So equal 2 times t plus 5 minus 1, or 2t plus 9, or yeah, plus 9. So there's another set. So I left a little bit more room here. So number 3, so another set. Maybe we let x equal 5t. You know, it can be anything, again, just as long as it doesn't restrict x. And then y would be 2 times 5t minus 1, which is 10t minus 1. There's lots of different, I mean, infinite number of possibilities for solutions here. All right, and then these, I should mention, in all of these, as t gets bigger, x will get bigger. T gets bigger, x gets bigger, t gets bigger, x gets bigger. So these would all trace from left to right, this line. All right, we have one more problem. I think I'm going to take a break where they do this one. It's kind of a long one. This one's an application. All right, we'll come back for that.